Hey, you know what time it is? Networking 101 time. Get on in the lab. You know, there's probably not too many technologies that could be considered the mother-in-law of the network, quite like spanning tree protocol, right? Kind of a necessary evil. You know, you love your wife, but there's something else that comes with it. You love the network, but spanning tree protocol also comes with it. So let's take a history look at what STP is, how it works, and so on and so forth, and really where it's going. Well, STP was actually invented by a brilliant lady that actually, she goes by the moniker, the mother of the internet. Rita Perlman developed spanning tree protocol. She was involved in the enhancements of spanning tree protocol. She's also designed a protocol that you may be familiar with in the data center side called Trill. It actually came out roughly around the same time, a little bit later, and stuff like that. She wrote a fantastic book that I highly, highly recommend every network engineer out there to read at least one time. I'd say a couple here because there's just a lot of meat to it, called Interconnections. But definitely take a look at that. Fantastic, fantastic book. Now, what is spanning tree protocol? Well, kind of in a nutshell, it's a tiebreaker. It's a loop breaker out there. And what we've done is that if you look at connecting a couple switches on a network here, you know, if you just got connecting two switches together, that's no problem, man, right? Just put a link between them and go on from there. But as you know that in any type of network design, one link, that's no good, man. We need some redundancy, right? So if you do something like this and you trunk these out, this is a problem. That's why we have technologies called Ether channel that are actually making sure that only one of these links are active at one time. Or basically, what it really amounts to is that I have one device will see one link active at one time, because you can't fool Mother Nature, certainly can't fool Mother Internet either. When you're designing this stuff out, I can only have one link through the network that's active, because what happens is, if I'm looking at designing this out, when I have a third switch or another switch in here and I go to connect these out in this loop, what you're looking at is, by plugging this other piece in, is your network starts to act a little bit quirky, right? You're having this side actually start announcing broadcasting through every port that it has, that it knows how to get to everything else except the port that it's connected to. Now another switch will pick this up and it'll broadcast it out every other port it's listening to, and then it'll broadcast this out, and you can see it spans, it gets bigger and bigger and bigger. And what's going to happen is that when you start doing this type of stuff, your switch starts to actually run away. You'll see your CPU, I'm drawing the screen, what a goober. You'll see you'll see your network really run away. Your CPU will spike really high. You'll see all your lights in here blink and get just go basically solid. I mean, you're really causing your own denial of service attack on the network. And truthfully, every engineer has to go through with it, right? It's an initiation test that all of us have to pass. We create this on a network, and it gets really bad when we start really building these big, massive diameter networks. And then it's easy to actually slip into this. Now, on 3 switches, you connect 3 switches together, yeah, you deserve a whooping. I mean, come on, man, you can't do that. But if you have 3,000, well, that's a little bit different story. Now, how does spanning tree work? Well, spanning tree was designed in a very hierarchical format, right? Where we have one root, one bridge, one switch that we call our root device. Now, this root device sets basically at the top of the network, or what we call the diameter. Every network spanning tree area is based on how many hops it has, and each hop is part of that diameter. Now, spanning tree protocol was actually based on a standard called 802.1d. And D is, if you ever look it up, it's one of the oldest standards that we actually have out there. Now, how we determine this root bridge is we either manually set it or it's hard-coded in here. And typically what it does is the lowest priority is going to actually be what we call the root bridge. Most every switch out there is going to come with a default setting of 38.464 as your default setting. And all it needs is just one step lower, and then guess what? That's your root bridge. Now, typically, as a best practice, you're going to set this root bridge to usually like 1 or 3, that something around those areas. I am a big fan of using odd numbers because I work with Rob and he's kind of odd, but that's just kind of how I like to design my networks out. You'll have your own methods and kind of go on from there. Now, your networks will then, since you have a hierarchy, since you have this top level switch sitting up here as your root bridge, it's going to make all the decisions on which links to block. And how does it do that? Well, if we just looked at a 4-switch design, this is what we call a 4-switch diameter, is what we're looking at is the switch is going to turn off basically the link that's furthest away from it. So it's going to calculate based on an algorithm, and it's going to say, oh, well, this one here is the farthest away. Now, part of this also goes into what we call cost, and cost is going to actually factor in link speed as well. So if it's a 10 meg link or up to maybe even a 100 gig link, that is going to factor in what my root bridge, how it's going to turn off and really basically decide what the diameter or how this traffic is going to flow on this network. Works pretty darn good. Now, the question that you get all the time is that what if I have switches out there that have the same priority? If I take these out of the box and I just plug them in, what happens? Well, you know, I mean, the folks at the IEEE, Raider Perlman and stuff, they have a pretty darn good sense of humor, believe it or not. And what you see is that in this type of design, they actually go through what we call root war. And root war is where since every switch has the same priority, is that they kind of have to have an election. They got to have kind of a fight-off, if you will. And it goes to the very next criteria. And the next criteria of root war would be who has the lowest MAC address. Now look, understand this really clearly, okay? The MAC address of the lowest MAC address on your device is typically going to be the oldest device in your network. If you're ever designing a network from scratch, or you're looking at implementing an SDP, on Cisco switches it's on by default, right? It's a great idea, should be on every network. I can think of very few reasons why it shouldn't be. Now, there are ways to work around it in the data center. We'll talk about that at a later date. But SDP is something we certainly should have. But because our deciding factor in a tie is the lowest MAC address on the switch, that is my oldest device here, and that is not good. So you always want to make sure that if your traffic is not flowing good, if you have some weird convergence issues and stuff, that you actually will determine, you know, well, who is the root bridge? Cisco devices is pretty easy. We can actually see who's root, who owns the diameter, if you will. And if it's an older switch, if it's like a 1900 or something, well, that's not good. You know, you want your root actually in the center part of your network as much as possible. Very, very, very important stuff. Now, real quickly, where does Spanning Tree get a black eye? Well, for Spanning Tree to calculate this stuff out, it has to go through a convergence algorithm, right? And that takes time, and it takes processing power. And you'll see there's a few different ways to build out Spanning Tree protocol. I'm going to explain the D version, then I'll just really quickly touch on the other ones that kind of touch this. When it comes to converging this out, when I'm looking at failing this over in a very simple design like this, click on another link, there we go. It takes time to move through and transition these states. Spanning Tree protocol is going to have multiple states it has to actually go through to figure out where to send this link up. If this link is up or down, or go through, forwarding, blocking, blah, 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 blah. And every manufacturer has to do this, right? No matter whose stuff you use, we go through. Spanning Tree is a standard. So what you're looking at when you're configuring this up is about a 30-second convergence time before your first packet flows through here. You see, this root bridge, it has to be able to talk to these other devices. And because none of these links are actually blocked, it sends out a special frame or special protocol called a BPDU, or Bridge Protocol Data Unit. This BPDU flows through the network, and there are two of them in Spanning Tree protocol, right? There's config change or config notifications, and then there's topology change. Config change is when we're actually designing what our root's going to look like. Topology is if I have a link or a switch drop off, and then the root knows it needs to recalculate everything in this network, right? So it takes about 30 seconds to actually work that out. There's a couple other algorithms that actually speed this up. There's 802.1W. W is the rapid converging Spanning Tree that takes that 30 seconds from 30 actually down to about 5 seconds. And it's good stuff. And it works really close to what D does, but it is a whole lot faster. And then you have really the preferred method that's really kind of going on today, which is S. S is actually building out your Spanning Trees virtually. So every VLAN on a switch. So if I have one switch here and I have, 3 VLANs on that, each one of these VLANs will have their own root bridge, right? So this VLAN here could be the root bridge of VLAN 1, but it could not be the root bridge of another device that I'd have over here. Let me go ahead and click that up. Maybe I got another switch here, and it's my green VLAN, and it's this device is actually the root bridge for that VLAN. And what it does, it gives me a little bit better control. It gives me ways to kind of adjust what links are on or off. So I don't have every single link blocked for every single VLAN. I can kind of craft my traffic, right? You can see how when you have this kind of design, it's definitely very relaxed and groovy because maybe this link is blocked over here in this VLAN, but in this VLAN, this very same link, it's all open and everything is good. And now you have 10 gig, 100 gig links that are not being wasted, waiting for a failure to happen. I can fold that traffic over and kind of shape it any way I want. And that's really the essence of what Spanning Tree Protocol does. There's a bunch of ways to do this. There's a bunch of different designs, but understand that the most critical piece here on Spanning Tree Protocol is just this. It's hierarchical design. I have a root bridge. That root bridge makes all the decisions based upon the network and what that diameter is. Priority determines who's going to be the root bridge. Not the newest switch, not the best model, not the fastest one. Spanning Tree has no idea what that is. The lower the priority, the winner in root war. And that's what you have to consider every single time. Every time I put a new switch on the network, I go through root war to figure out who is the lowest priority on the network. And there's enhancements that have been made on here, like W, which is an important enhancement, and then certainly S is probably what you'll deal with absolutely the most on a network. But I'll tell you what, I can't think of a single time as a network engineer in 25 years of doing this job that I've ever went in there and really tweaked with the timers on STP. They say don't do it. I have not found an advantage to actually tweaking those timers. I've actually found many disadvantages to messing with them. It's something I don't mess with. It's typically something that you probably won't have to touch, most likely. So take it kind of as it is and roll with it from there. Great advancements in STP. We're doing actually really cool designs to kind of get rid of this, but STP is the root part of the Ethernet, right? It's always going to be there. You have to find ways to work with it or to work around it.